We have Carolina Ortega Perez, who's going to be talking to us about encrypted access logging.
Thank you. Hi, I'm Carolina. I'm a PhD student working on the intersection of applied cryptography and tech abuse prevention. I work on building systems that provide privacy, transparency, and accountability for users. And the work that I will be presenting today, encrypted access logging for online accounts, is joint work with Ala Dafala and Tom Ristenport. And we're all in the room today. I have pictures in the end. So nowadays, we all have multiple accounts for all sorts of services. And what happens in these accounts has a big impact in our lives. And while there are a lot of benefits to these accounts, as most things in life, they can be leveraged to cause interpersonal harm. So back in New York City, I am a volunteer at CETA. This is the Clinic to End Tech Abuse. And there, we work with survivors of intimate partner violence, or IPVs for short, with tech concerns to help them regain a safe digital environment. One of the main tech abuse issues faced by IPV survivors is account compromise. This is when abusive partners gain illicit access to their accounts. So, and in IPV situations, oftentimes the abusive partner knows the survivor's password and can authenticate as them. So at CETA, one of the main things we help survivors with is with account security checks to see if an abusive partner has gotten access to their account, and this is very important for their safety. So in an appointment, we have the survivors log into their accounts and then access their account security interface, or ASI for short. ASIs are interfaces like the one that you can see here, where one can see the activity on the account, which devices it has been logged in at. And so the idea is that if an abusive partner who authenticates as the user logged into the account at some point, then during the appointment, we would find an entry about it. And then depending on the situation, we might suggest removing the malicious device and changing the password. And this way, ASIs are very important in our appointments, but also for users in general, to verify their account safety and detect potential compromise. However, ASIs are very easy to spoof, as shown by Dafala et al. In 2023. So back to our diagram, the information that is sent during the login is actually an HTTP request, which includes the login information and a string that is called the user agent. And then the platform uses the information from this user agent to then display in the ASI. But the string, the user agent, is actually very easy to change. Using, for example, in browser developer tools, that's a couple of clicks. You can just tamper with the string. And the abuser can change the user agent to, for example, match one of the user's devices. Recall that it knows the survivor's phone model, so you can just modify it to that. And then when the real account owner checks the ASI, it is going to see the same entry twice. And this is very confusing. And this hinders ASIs from meeting the goal of enabling users to see their history of their account and detecting malicious activity. So ASIs have an integrity problem. And in this paper, we explore whether we can involve the operating system to resolve this. So in our protocol, we propose client-side encrypted access logging protocols, or CSAL for short, to provide device attribution. And so CSAL protocols are agnostic to the authentication mechanism, and we do not rely on external services, but we do require operating system support because we consider browsers as an untrusted party. In our paper, we provide a formalization of CSAL protocols. We detail a protocol and prove that it satisfies our security definitions, and also report on a proof of concept and discuss some deployment challenges. So going back to our diagram, a first idea is to involve the operating system as a trusted party. So you can send the same information as before, but also an additional device identifier that is signed by the operating system. So, for example, we can send like device ID 1, device ID 2, and you can think of this being like, for example, a serial number, something that is provided by the operating system and the user cannot tamper with. And so the server stores the same information as before, plus this device IDs. And when the survivor requests the ASI, it gets the same information as before, plus these device identifiers, which serve as a ground truth to the user. And everything seems kind of okay so far, except that we're revealing these device identifiers to the server, and that is not a good idea. So as I mentioned before, we were thinking this could be static identifiers like a serial number, but there is a really long literature on device fingerprinting and avoiding device tracking and how we should not send static identifiers to platforms. So here, for example, advice for Android users. Tip number 1, use something that's user resettable. So like in general, we don't want to use static identifiers. And so Android and Apple, they have spent been restricting access to static identifiers for more than 10 years. So we definitely do not want to roll back on that. So we're going to add the server to our thread model. And so the new goal is also we want the system to provide privacy from the service provider. So to recap, in our thread model, from the computational perspective, we're considering a malicious browser or app in the client side that is not trusted to provide neither integrity nor privacy. And then a semi-honest server that wants to learn the unspoofed device information. And it's semi-honest because we actually cannot prevent man-in-the-middle attacks in this paper, but I'll talk more about that later. And we have the malicious user, which wants to tamper or circumvent registrations into the log. And recall that it can authenticate as a user. It is possible that previously the user had logged into the device of the abuser, and all this to say there are solutions to sometimes account compromise prevention, but those might not cut it out in this scenario. We also need tools like ASIs to detect and mitigate compromise after it occurs. And so to tackle this, we're going to rely on operating systems to do encryption and signing for users. And we assume that the OS is completely trusted. So back to where we left off. Users now have some keys that are created in the operating system. So there is a public-private key pair and a symmetric key K1. And so during logging, they're going to send logging information, user agent as before, but also the public key, PK1, and we'll use the symmetric key to encrypt the device identifier and send that ciphertext. The server now stores the ciphertext of the device ID and also stores this public key. And then when the second user logs in, wants to log in, creates a new set of keys. And now things change a little bit. We'll have an extra round trip where the user first authenticates to the server. If that succeeds, then it gets the set of public keys associated to this account, in this case like PK1, and then the session sends back the public key, the user agent, the encrypted device ID, and it would also encrypt the symmetric key under the public keys that it received. And all of this information is stored at the server, including now ciphertext of symmetric keys. And so when the user comes back online and requests its ASI, the server sends back the log of all the ciphertext, and the user can decrypt it all and has the same view as a couple of slides before with the user identifiers. So it seems like the user can recover all the entries. The server cannot learn the device IDs because they are encrypted. And the malicious user cannot tamper with the entries because it cannot tamper with the keys because they are in the operating system, and that part is trusted. Yeah?
Is it an issue that the server could add device identifiers because it could pick a key and use a public key that's uploaded, or is it outside of your practice?
Yes, so you mean like adding fake entries into the log?
Yeah.
That would be an issue because it would be like confusing to users. Yeah, it is outside of our threat model, but yeah, it would be bad. Okay, and so here, going back to this, what happens if we have like a setting that is a bit more complicated to what I just described? So this is the same flow as before, have a logging from 2 different devices. And what happens if now the account owner has a third device? And so first it logged in from a computer, and now it's logging in from the cell phone. And so similar to the second login, it first authenticates, gets the set of public keys, encrypts the device identifier. This time it encrypts the symmetric key under both public keys. So one ciphertext for device 1, one ciphertext for device 2. But then the server stores all of this information. But then when it requests the ASI, it's only going to be able to see the device identifier for its own device. It doesn't know the keys to decrypt the other ciphertexts. On one side, from the user side, this is the same as the status quo. We still have the user agent, so we're doing not worse than what there currently is. But can we do better? It seems like fundamentally, you cannot decrypt the other entries if none of the other devices come back online. But if, for example, the first device reconnects, then it could re-encrypt some of the information that it knows to the newer sessions. And so this allows the device to share keys it knows with newer devices that don't know this information. So yes, this device 1 can re-encrypt key 1 and key 2 to the other sessions. And this is stored by the server. So then if device 3 then asks for ASI after the re-encryption, it can decrypt everything that is in the log. This is most part of the protocol. We have some more stuff and more details in the paper. And I'll say here I'm mostly using logging as an example of everything that is stored in the ASI, but we could actually think of having other information stored. Maybe, password changes or something should also be stored in the log for forensic reasons to help users detect what is going on in their accounts. Okay, so moving on to the formalization, we have 3 security definitions. We have log privacy and session unlinkability against an honest but curious server. So privacy means that it's not able to read the device identifiers. Session unlinkability, we defined it as not being able to detect whether 2 sessions are from a same device or from 2 separate devices. And we also formalize this idea of ability to access the log, which is about being able to decrypt some amount of entries in the log. Yes?
I was going to ask for is your goal that you can't even recognize when the same device comes back again, or are they like fresh encryptions random encryptions every time? The DIDs. So like if the same DID shows up multiple times in the log, do you want to hide that, I guess?
So I guess the same DID, if it is like from a same session, if it has like this same cookie, for example, the server would know that is like the same session. If it's like different sessions, yes, that is, we formalize a session unlinkability as, not being able to tell the 2 separate. So yeah, it's some randomness. Okay. And so, I guess back to like what I was mentioning during like the re-encryption, we do have a theorem that says that you cannot have full privacy and retrieve all of the log entries. And a simple way of thinking about this is like if you have a device, you only use that device, and then that device falls into the lake. And then you buy a new device, but you cannot decrypt the older entries because the keys that you need to decrypt the previous ciphertext are in the bottom of the lake. So that information is gone forever. There's the opposite. If nothing is encrypted, then you can recover everything, but then there is no privacy. So yes, privacy and full access to the log, not compatible. And good, so we define this a reachability graph. This is a graph where each of the nodes is a session, and there are edges from older to newer sessions. And when there is a re-encryption, there are edges from the session that are getting re-encryptions to the session that did the re-encryption. And there is a final graph that is taking the transitive closure of all of this. We prove that assuming that there is secure encryption, the protocol that I described before meets the privacy definitions, and the ability to access the log is characterized by that graph that I mentioned, with the conjecture that the ability to access the log, that the best that you can do is this graph while maintaining full privacy. That is the main protocol, but there are some loose strings regarding the setup. So let's zoom out a bit and talk about the architecture. How could like a CSAL protocol be deployed? So if we go back to our running example, we said there is the operating system that is trusted, there is the malicious user that cannot tamper with this, and it sends information to the server, sends like some payload, includes ciphertext, and I mentioned a scheme like it is signed by the operating system, but the operating system is actually not directly talking to the server, right? In the middle, we have a malicious browser, which is untrusted, and so what would happen if the browser tries to do an active attack? Like, where are the keys that sign the operating system if we're coming from? How do we know that the browser is not tampering with everything? And so to protect against a meddler in the middle attack by the browser, we need to authenticate the operating system and the server. But how to do so? So we have a couple of ideas. So let's first talk about the part of authenticating the operating system. So we model our architecture based on the FIDO2 framework. So FIDO2 is this group that's been working on probably most famously passkeys, and they have the WebAuthn spec details how it's an API detailing how to register and authenticate users using an authenticator. And so the way how it works is devices have an authenticator. So for example, like the biometric recognition that's available in most devices these days. And this authenticator is certified by the vendors that produce it. And so in WebAuthn, there is an initial registration phase where the device, the authenticator creates the keys and sends the public key to the server, along with a certificate to attest that this is a real key created by an authenticator created by a valid vendor. And then when the user logs in, it sends a request to log in, then it gets a challenge from the server, and then it signs the challenge using the secret key from this key pair. And so the server verifies that this is true and that you authenticate to the server. Maybe this discussion, this explanation may have given a bit of a hint of why we decided to model our system after FIDO2. So basically, this is a multi-year effort work where there was a lot of like collaboration across multiple parties in industry. This authenticator is already handling some sort of cryptographic keys, and it's been widely deployed. And so our idea is to extend the authenticator to also be an encryptor. So, creates the signing keys, but also the encryption keys. And then it registers the public encryption key with the server as well. And then when the server distributes this to other sessions that are logging into this account, and so if this device were to log into the account, it gets the set of public keys associated to this account and then encrypts the information under the keys in this set of public keys. All right, so from an OS side, we propose a FIDO2 style architecture and rely on FIDO2 type certificates to have authenticity for the keys for the authenticator and the encryptor. Now from the server side, authentication, we don't delve very deep on this in our paper, but we envision something like, for example, an infrastructure similar to TLS certificates, where they can also be a whitelist of servers to encourage them to behave well. And so these two ideas, we can prevent attacks against a malicious browser. We cannot really prevent meddler in the middle attacks from the server. We're not sure how to do that. So that's why I've mentioned we're addressing a semi-honest server. And yeah, there is like future work needed to prevent this type of attacks. We have a bit more discussion of like a malicious server threat model in the paper. So if you're interested, check that out. And now we have a proof of concept for our CSAL protocol. This is a Python implementation of the server, client, and encryptor in different processes. At a high level, during logging, we have like some payloads that are a couple thousand bytes going like from the device to the server, and then from the server back to the from the server to the device, first like sending the public keys, then from the user to the server, like with the ciphertext and all this information. Time-wise, it takes 146 milliseconds in our experiments if you have a single session. And then, for log retrieval is accessing the ASI. This happens with less frequency. We had a report on like 2,600 bytes for a single session. All of these numbers like grow if you have more sessions. But the takeaway of this is performance-wise, things like the system could be practical. We were not really hyper-optimizing here for the performance. And we think that the hardest part on all of this is actually like this collaboration with like operating system vendors and how to figure out the full architecture. And so for future work, as I mentioned a couple of slides before, we do have some suggestions for all this architecture and collaborating the FIDO2 and the certificates and how like handling the different parts of the ecosystem, but there's clearly a lot more work to do in this. And collaborations with OS vendors and platforms are definitely challenging, not trivial, will take probably multiple years. We've seen something similar happen with like FIDO2, so there's some sort of hope that this could be possible in the future. And since we base a part of our system on like FIDO2's architecture, maybe we can even like reuse part of the FIDO2 specs. Some other areas for future work, as I mentioned, more formalization and protection against malicious server would be very important. We also need more work to understand what are potential risks of ASIs. We do believe that the benefits, like the forensic benefits of this outweigh potential risks of, if the server, the survivors are able to see like an ASI that has integrity, but like so are the abusers if they can authenticate as the user. But it's probably more important for the survivors, but it's always good to look into these things. And also on the user side, what type of information should be included in the ASIs? We were using the example of serial numbers, but like what is better, what's more practical, what is more useful for users. And so that was my talk. Thank you for listening, and I'll take questions now.
I wonder how your work compares with alternative approaches, and I have two questions related to that. So you said your motivation was the victims of abuse, and you have a malicious device on your account, right? Mm-hmm. And you also recommend them to change their password. Mm-hmm. And in my experience, what happens whenever you change a password on an account, all devices get logged out anyways, right? So I wonder, and does that address the concern sufficiently? And then related to that, are there maybe other applications where your approach could become useful?
To the first question, ideally, yes, if you change a password, everything changes. That not always happens. Okay. Yes, and yeah, like the work that we do in the clinic. Sometimes we have like clients that have like changed the password, so sometimes we see like, oh, this device, there was a device that was logged in, but now it seems like it logged out, and oh, that is like around when I changed the password. But like some clients maybe like don't think of this. So yeah, that's why we talk about all this security advice with them, and ideally just changing a password would be good, but sometimes the implementation doesn't go as expected. And then other uses for this, I think like the system is very flexible. Yeah, we're thinking more like accounts and yeah, as I was saying, like you can start like other types of information that is not only logins, and I don't have any particular good idea right now, but it's, yeah, it doesn't seem like very restricted to like the specific use case. And I don't know, even like the encryptor, maybe you can encrypt other stuff that doesn't have anything to do with logs.
Thanks.
Okay, thank you.
So my question was connected to your future work. You were mentioning about other risks. So the location usually is something very useful feature for the users to get to know if the other devices are. And I understand that the attacker can also fake the location and all these kind of things. But my question is more, what can the attacker learn from the location of the victim that could also pose a risk? Like get to know maybe where, if there was a previous relationship, maybe a broad location can get to know if the victim is at work, at what time usually they log in, and if your framework could also be applied to somehow encrypt the location so that maybe just the victim or one of the devices can get to access it, and the other, and some kind of like, I don't know, how is it that we can protect as well?
Yeah, that's a good question. So yeah, I think drawing back, from my experience working at the clinic, so you have like different types of clients, and some of the people, still live with the abuser, and so like a place like where they live, maybe it's obvious, but maybe like, oh, you told me that you're not using like this social media anymore. Why do I see you connected? Something like that could be bad, if you see something connected. But on the other hand, we do get like some clients that luckily have now live in separate households and are trying to like rebuild their life, and oftentimes do not want to for the abusers to know where they are located, and so like in this sense, like learning the location would be bad. I'm sorry, what was your second question?
If you said that your framework is very broad, and I was wondering how you could maybe apply your framework to somehow protect the location.
Oh yeah, yeah. So I guess like the main part here is there is information that I guess we see this as like there's like a plain text part of this that is like this information of the user agent, and if like the browser is already like sending that location, would have to like convince services or something to not collect this information and collect it over there. And then like in the ciphertext, we can always like encrypt this. Like we can have like the operating system, if we assume that the information that is encrypted is trusted, just include it there. And like attest to it and be like, yes, this is like the real location as a root of trust, depends on like what is being trusted. But yes, if it is like being sent by the browser, again, it doesn't have integrity, but you can decide whether or not to trust it.
Yes. Go ahead. So I have a question about how you were using the authenticator. I didn't quite catch it from your slide. So in your scenario, when, like, how frequently would you be using the authenticator, or did I misunderstand that?
Yes. So the authenticator as like demonstrating. I guess I can go back. Okay. So in general, like the authenticator is deployed, when you're like logging in, if you log in with like passkeys or something like that. And so we're just thinking like we can add to this. The authenticator is generally only used for logging in, so one-time thing. In most of the examples, since we're also like adding the ciphertext during the moment of login, so it would be like at this initial stage when you're connecting first to the session.
So my question is about whether you're assuming in your threat model that the abuser has access to the authenticator, and if the abuser has not, isn't then the problem maybe already solved because you just log in using your authenticator? So maybe I misunderstood something here.
So I mean, if the so we do assume that like different devices have different different keys, and oftentimes in like right now there's a lot of effort on rolling out pass keys, but like generally you can still like log in with a password. It says like, oh, like do you have a pass key? If not, try other methods or a recovery email or this type of information. And so here, I guess since I was talking about the authenticator, I was just like demonstrating you authenticate with the authenticator and the pass key, but actually it could be possible to not use the authenticator and only use the encryptor. Like this could be, instead of being like login child or something, you just send like username and password, and then the server says, okay, here are the public keys, and then this, and like skip this way. This is like a different like method of authentication, and we're agnostic to that in the CSAL protocols.
Okay, maybe offline I'll ask you with some more details,
Okay.
but there were another questions.
Ron, did you have a question?
It was a similar question about authenticator, so.
Okay.
Maybe I missed the privacy goal here, but isn't the encrypted device ID also a device ID? Can we use instead of the device ID?
So I guess like we have the idea is to not have like something that is static. Like the bad thing that we should not be like providing to services is like a static identifier that you can use. Like if I log in now and if I log in like in 5 years, like you will forever know that it is me. And so if this is like an identifier per session, it would be fine. It also has like the cookies and this type of thing. Like, oh, this is like still the same session that you're connected. Yes.
Oh, so the logs on the server side keeps building up every time there's a new session?
Yes.
Ah.
Yeah. And then
Okay, so I have multiple device IDs for the same device,
uh,
unless I track it by the public key that's uploaded from the same device.
you have multiple ciphertexts for the device ID, but I did like a single device ID. There are, I think multiple platforms sometimes let you see the last 90 days and this type of thing, so it might not go forever.
Privacy goal? I think I missed it. Can you reiterate?
Yeah,
I'm
we
just trying to-
don't want the server to learn unspoofable information. Like basically, for example, like a serial number that's like a static identifier that the user can never change, and that you could use to like track the user forever.
That server only. I see.
Yes.
Got it. Okay. Thank you.
Okay.
Let's thank Carolina again. We can take more questions.
Oh, there were questions in the chat.
There's one question and then one remote
Do
question.
we have time? Is it just me?
Is there a question online?
Babu, can you come off mute?
Can you guys hear me?
Yes.
Okay. My question is related to more towards the feasibility of this implementation, because you said the browser is not trustable, right? You can't trust the browser. And browser wants the protocol, typically application. Operating system provides only the transport. It can provide a library, HTTP library, but if you look at the browser implementation, they don't have to necessarily use the operating system provided library for HTTP protocol implementation. So if you want operating system to insert the device ID, I don't know how that's going to be feasible. Like Chromium has its own HTTP library, and if you don't trust the browser, then there is no way operating system can insert a device ID in the protocol.
Yeah, we do assume that like this would require like a lot of like support and like collaboration with like platforms and operating systems and establishing channels that don't currently exist. I think we're out of time, so I'm happy to answer questions later. I'm on Teams, so you can message me there too. Yeah.